This is lesson 7.1, and we're going to be talking about balancing chemical reactions. Our goal today is to learn what a chemical reaction is, what the different reaction symbols mean, and how to balance a chemical reaction. At the end, we're going to go through several different examples of how to balance a chemical reaction, and be sure to watch the entire video because I'm going to share 5 different tips with you throughout the video. All right, let's just start off and answer the question, what is a chemical reaction? A chemical reaction is a rearranging of how atoms are bonded. And so in a chemical reaction, some bonds might be broken, some bonds might be formed, some bonds might change somehow, but the atoms themselves never change. All right, in a chemical reaction, one element can never change into a different element. Atoms aren't destroyed, atoms aren't created. Simply, the elements are going to change how and with what they are bonded. When a chemical reaction takes place, you may see some of the following, although not necessarily. You might have some heat being given off or absorbed, so you might see some temperature change. You might see a color change or some kind of appearance change of the stuff that's involved. You might see a precipitate being formed. A precipitate is basically a solid that forms in a liquid. You might see a gas being given off. It might be bubbling off, or you might see some kind of fumes being given off during the reaction. You might have some flames, or you might have smoke during the chemical reaction. And most likely, you're going to have some sort of change in the properties of the chemicals that are involved. So after a chemical reaction is taking place, the chemicals that you make in the chemical reaction, that is the products of the chemical reaction, are going to have different properties than the reactants or the chemicals that you started off with. Now, sometimes those change in properties are not going to be easily observable to your naked eye. You might need to use some sort of sophisticated equipment in order to be able to observe some change in properties. And keep in mind that all of these different evidences of a chemical reaction are not necessarily proof that a chemical reaction has taken place. In order to really know that a chemical reaction has taken place, you need to actually know that the atoms involved are changing how they are bonded. So you could, for example, notice that you have some sort of change in the temperature, but it might not necessarily be a chemical reaction. There's other processes, for example, dissolving some solid in a liquid can sometimes change the temperature of the liquid, but that doesn't necessarily indicate that a chemical reaction has taken place because all you've done is dissolve that chemical. You haven't actually changed the bonding in that case. So all of these need to be taken with a bit of a grain of salt. You need to recognize that these are evidences of a chemical reaction, but they don't necessarily prove that a chemical reaction has taken place. There is one thing, however, that's never going to change during a chemical reaction, and that is the total mass of all the chemicals involved. In a chemical reaction, the mass of all the chemicals is going to remain the same. That's known as the law of conservation of mass, and people have tested this again and again and again, and always noticed that the mass of the reactants and the mass of the products is equal, as long as you weigh all of the reactants and all the products. And the reason that the mass of all of the chemicals involved never changes is because the exact number and type of atoms never changes in a chemical reaction. So all the atoms that you start off with are all the atoms that you end up with. The only thing that changes is how those atoms are bonded. So you can see in the balance over here, for example, if you do a chemical reaction between oxygen and hydrogen, before you do the reaction, what do we have? We have 4 different atoms of hydrogen. These white spheres are hydrogen. And you have 2 atoms of oxygen. After the reaction takes place, you still have 2 atoms of oxygen and 4 atoms of hydrogen. However, they've changed how they're bonded, right? To start off with, the hydrogen is bonded to hydrogen, the hydrogen is bonded to hydrogen, and the oxygen is bonded to oxygen. And after the chemical reaction, you have the oxygen bonded to hydrogen, and this oxygen bonded to hydrogen and hydrogen. So they change how they're bonded, but the exact number and type of atoms hasn't changed at all. And that's why the mass of the reactants is exactly equal to the mass of the products in any chemical reaction. A chemical reaction can be represented by a chemical equation. And so up here at the top, we see that this is a chemical reaction between magnesium and oxygen. And when they react together, they're going to form magnesium oxide, which is the product here. And I want to just tell you guys a little bit about different aspects of this chemical equation. First of all, this arrow here tells us that a change has taken place. All right, the arrow is the chemical reaction arrow. Everything to the left of the arrow is known as the reactants, and everything to the right of the arrow is known as the products. These subscripts here, or these little numbers that you see, this O2 here, this subscript refers to the number of that element in the molecule or unit. When you're balancing a chemical reaction, never ever change these subscripts, because the subscripts indicate what chemical you have. And so you don't want to change the subscript and therefore change what chemical reaction that you have that's taking place. The big numbers in front of the formulas of all the different chemicals are called coefficients. If you don't have a coefficient, for example, right here in front of O2, there's nothing. If you don't have a coefficient, it's implied that the coefficient is just 1. These coefficients here are the only things that we're going to change when we balance a chemical reaction. And how do they work? Keep in mind that these coefficients multiply every element in the chemical. So for example, up here, when you have 2 MgO, that means we have both 2 magnesiums and 2 oxygens on the right side of this chemical reaction. Let's try something a little bit more complicated. For example, if you have 3 calcium nitrates, we have, well, first of all, each calcium nitrate has 1 calcium. So that means we have 3 calciums in 3 calcium nitrates. And also, each calcium nitrate has 2 nitrates. Each nitrate has 1 nitrogen. And so in this case, we have 3 times 2, or 6 nitrogens in 3 calcium nitrates. Now, what about oxygen? Pause the video and think about how many oxygens you have here in 3 calcium nitrates. All right, that's right. To do the oxygen, we're going to multiply 3 times 3 times 2 in order to get 18 oxygens here. Remember that numbers outside of parentheses multiply by everything in the parentheses. And remember that coefficients out here multiply by everything here in the formula. And so to get oxygen, it's going to be 3 times the 3 here for the subscript for the oxygen times the 2 here for the subscript of the nitrate. Additionally, you're going to notice these different letters after each of these chemicals. What do you think those are? It turns out that those represent the state of the chemical. So S stands for solid, L stands for liquid, G stands for gas, and AQ stands for an aqueous solution. So anytime you have AQ, it means that chemical is dissolved in water. In this case, the magnesium here is a solid, oxygen is a gas, and magnesium oxide is a solid. Now remember what we said before about the law of conservation of mass. The mass of the reactants must always equal to the mass of the products. Because the atoms involved are not created or destroyed in a chemical reaction, a chemical equation must always be balanced. And what in the world does that mean? Basically, that means that the number of each of the elements must be the same on both sides of the equation. The reason we do this is not just because chemists like to organize things or like to make things nice and neat. The reason is because this is what actually reflects what happens at the chemical level. Atoms are not created or destroyed, and we need to reflect that in the balanced chemical equation. So when your teacher makes you balance a chemical reaction, it's because that's what the atoms themselves are actually doing. So let's see if this reaction right here is balanced or not. Notice that there are 2 magnesiums on the left side, right? This 2 here in front of magnesium means we have 2 magnesiums on the left side, and there are 2 magnesiums on the right side. This coefficient in front of magnesium oxide tells us there are 2 magnesiums on the right side. What about oxygen? Is oxygen balanced? Yes, indeed. Oxygen is balanced too. This 2 subscript means we have 2 oxygens on the left side, and this 2 multiplies through by both the magnesium and the oxygen. And so we have 2 magnesiums and 2 oxygens on the right side. And so both oxygen and magnesium are balanced in this chemical reaction. If every element is balanced, then the reaction itself is balanced. If even one element is not balanced, then the reaction is not balanced. So make sure that every element is balanced when you balance a reaction. Now, I would like to represent this reaction a slightly different way just to show you guys what's going on with the atoms involved. What does this 2 here really mean? This 2 here means that we have 2 magnesium atoms that react with, well, of course, remember, there's no number here, so that means there's only one O2 molecule. So 2 magnesium atoms react with 1 O2 molecule, and this 2 here is because there's 2 oxygen atoms per oxygen molecule, and when they react, they're going to form the ionic compound magnesium oxide. and we have 2 magnesium oxides as our product. Each magnesium oxide has 1 Mg2 plus and 1 O2 minus. Notice that we have 1, 2 magnesiums here, 1, 2 magnesiums here, 1, 2 oxygens here, and 1, 2 oxygens here. All right. So you can see that each of the elements is balanced in terms of each of the element has exactly the same number of atoms on each side of the equation. Now, let's go ahead and try out a couple different sample problems so that we can see how this works. We're going to start off easy, and then we're going to go to harder and harder problems. This is a classic chemical reaction. It's the chemical reaction between sodium and chlorine gas, and when they react, they're going to make sodium chloride or ordinary table salts. So when we're balancing this, we can notice that, well, first of all, we have 1 sodium here and 1 sodium here, and so sodium is already balanced. So let's go ahead and look at chlorine. On the left side, we have 2 chlorines because we have this 2 subscript here, but on the right side, there's only 1 chlorine. So chlorine so far is not balanced. How can we balance it? You might be tempted to do this. You might be tempted to put a 2 after NaCl to make it NaCl2, and that would probably be the fastest way to balance this chemical reaction. However, that would be completely wrong. Remember, never, ever, ever change the subscripts when you're balancing a chemical reaction. Why is that? Because that would change the chemical here. Table salt's not NaCl2, table salt's NaCl. And so you cannot change the subscripts whenever you balance a chemical reaction. You will automatically get it wrong if you ever change the subscripts when you balance a chemical reaction. So how do you actually do this? Well, if you can't change the subscript, what can you change? The coefficient. So we have to put a number out here that's going to give us 2 chlorines. And so if we put a 2 out here in front of NaCl, that 2 is going to give us 2 sodiums and 2 chlorines. And so now our chlorine is balanced. However, you've probably noticed, well, that's going to mess up our balancing of sodium. Now we have 2 sodiums on the right side, but we have only 1 sodium on the left side. So what do we do about that? Once again, what we can do is we can change the coefficient in front of sodium. We now have 1 sodium, so all we need to do is change that to a 2 in front of sodium. And now we have 2 sodiums on the left, 2 sodiums on the right, and that chemical reaction is totally balanced. All right, let's try another one. In this chemical reaction, nitrogen gas reacts with hydrogen gas to make ammonia gas, or nitrogen trihydride. Now, there's a couple different ways that we could balance this. First of all, notice that both nitrogen, here there's 2 nitrogens, and here there's 1 nitrogen, and hydrogen, here there's 2 hydrogens, and here there's 3 hydrogens, so both elements are not balanced. You could start with either one. You could first balance the nitrogen, and then balance the hydrogen, but I'd rather start with hydrogen in this case just because I want to show you how this is going to work. Notice that we have 2 hydrogens on the left side and 3 hydrogens on the right side. So at first, this might seem to be a bit challenging. What do you do when you have 2 on one side and 3 on the other side? There's no one single coefficient that we could add here or here that's going to balance the reaction. So if a single coefficient will not balance that chemical reaction, the amounts themselves become the coefficients for the other side. What do I mean by that? I mean that this 2 right here is going to become the coefficient for this ammonia here, and then this hydrogen here, the amount of hydrogens you have on the right side, is going to become the coefficient on the left side. And that is going to balance out the reaction every single time you do it. Why is that? Because 3 times 2 must be equal to 2 times 3, all right? And so this is going to work anytime you have, for example, 2 and 3, 3 and 4, 2 and 5, or anytime one single coefficient doesn't work, you're going to need to put coefficients on both of these, and whatever amount you have over here becomes the coefficient over here, and vice versa. And so now in this case, we have 3 times 2 is 6 and 2 times 3 is 6. And so both sides have 6 hydrogens. In the process of balancing hydrogen, notice that we've also balanced nitrogen. On the left side, we have 2 nitrogens, and on the right side, we also have 2 nitrogens. And so this is the balanced chemical reaction for nitrogen reacting with hydrogen to make ammonia. Let's try another one. Here we have a little bit more complicated chemical reaction. We have 4 chemicals total. We have 2 on both sides, and we have a lot of stuff going on. Notice that we have oxygen in every single chemical, and that oxygen is going to be dependent on how we balance everything else. So in cases like these, first balance the element that is in the least number of chemicals. And then last, balance the element that is in every single chemical. So pause the video and think about, what should we balance first? That's right, we should balance hydrogen first because there's hydrogen in this chemical, and that's it. Hydrogen's only in 2 different chemicals. Because hydrogen is only in 2 different chemicals, it's going to be a lot easier to start with hydrogen. Let's check it out. On the left side, we have 2 hydrogens because of this subscript right here. And on the right side, we have only 1 hydrogen because there's no subscript or no coefficient in front of HNO3. And so the only way that we can balance this hydrogen here is to put a 2 right here in front of HNO3. That's going to give us 2 hydrogens on both sides of the equation. Now pause the video and think about, which element should we do next? If you said nitrogen, you're correct. We want to save oxygen to last because oxygen is in every single chemical. And because nitrogen is only in 3 chemicals, we're going to do nitrogen next. Now notice, how many nitrogens do we have on the left side? Here, we have only 1 nitrogen on the left side of the reaction, but on the right side, we have 2 nitrogens here in this chemical and 1 nitrogen right here in this chemical to give us a total of 3 nitrogens on the right side of the reaction. So in order to balance the nitrogens, what do we need to do? That's right, we need to put a 3 in front of NO2 over here on the left side. That's going to get us 3 nitrogens on both sides of the equation. Now let's check out oxygen and see if it's balanced in the process. On the left side, how many oxygens do we have? We have 3 times 2 or 6 oxygens here, plus 1 oxygen from the water to give us a total of 7 oxygens on the left side. What about the right side? On the right side, we have 2 times 3 or 6 oxygens here, plus 1 oxygen right here to give us a total of 7 oxygens on the right side. In the process of balancing the hydrogen and nitrogen first, we've also balanced oxygen in the meantime. So this is all done. All right, let's try one more chemical reaction. Here we have ethane is going to react with oxygen to make carbon dioxide and water. This is a complete combustion reaction, and these can be a little bit tricky to balance. But keep in mind, just follow this step-by-step process and you can do it just fine. Pause the video and think about, which element should we balance first? If you said carbon, you're correct. Or if you said hydrogen, you're also correct. But if you said oxygen, that's wrong. We're going to save oxygen till last because oxygen is in 3 different chemicals, whereas carbon is in only 2 and hydrogen is in only 2. So it doesn't matter whether you balance carbon first or hydrogen first because they're both equally simple. I'm going to go ahead and start with carbon, but you could start with hydrogen. Just don't start with oxygen. On the left side, notice that we have 2 carbons because we have a 2 right here. On the right side, we have only 1 carbon. So once again, we're going to put a number right here in front. A coefficient of 2 is going to balance the carbons. So now we have 2 carbons on both sides of the equation. Next, let's go ahead and balance hydrogen because we want to save oxygen till last. How many hydrogens on the left side? That's right. We have 6 hydrogens on the left side, but only 2 on the right side. So how can we balance it? Pause the video and think about what you're going to put right here in front. We're going to put a 3 in front of water because 3 times 2 is 6, and we have 6 hydrogens over here. And so once you put a 3 in front of water on the right side, we're going to have 6 hydrogens on both sides of the equation. Now, let's go ahead and do oxygen. On the left side, we see that we have only 2 oxygens there, but on the right side, look at all the oxygens we have. We have 2 times 2 or 4 oxygens here, and we have 3 oxygens here. And so that's going to be 4 plus 3, or a total of 7 oxygens on the right side. Now, what number can you put in front of this O2 in order to get 7 oxygens on the left side? Well, in this case, we cannot put any whole number here to balance the oxygen. And so the last tip that I'm going to give you guys is that if all other elements are balanced, you may temporarily use a fraction to balance the last element. And in this case, we're going to want to put a 3.5 in front of oxygen here because 3.5 times 2 is 7. And we have 7 oxygens on the right side, and now we also have 7 oxygens on the left side. However, you don't want to leave that 3.5 there. You want to turn everything into a whole number. And so what you can do is you can multiply every single coefficient by 2 in order to get rid of that fraction. And so here, 2 times 1 is 2. And so this new coefficient is going to be 2. 3.5 times 2 is 7. 2 times 2 is 4. 3 times 2 is 6. And so each of those new coefficients is going to be 2, 7, 4, and 6. And now the reaction is still balanced, and we've gotten rid of our fraction. All right, that's it for today. Have a great time balancing chemical reactions. See you here next time. Stay curious.